17.4 Decision Making Under Risk. In the previous section, you learned how to make a decision when the probabilities of the states of nature occurring were unknown. You are now going to learn how to make a decision where you do have this probability information. To do so, you will use a technique known as decision making under risk. To demonstrate the decision making under risk technique, consider the following example. The women's retail clothing market is defined by very distinct, short-selling seasons throughout the year, perhaps because women are more attuned to clothing trends than men. Christine is a buyer for Gimbel department store, and her job is to decide how many Nicole Miller dresses to purchase for the upcoming fall season. Ordering too few dresses will result in lost sales, whereas ordering too many dresses will result in the store having to deep discount any unsold dresses at the end of the season. Christine needs to place her order well before the fall season begins, and she will not have the opportunity to reorder additional dresses at a later time. To simplify this problem, let's assume that Christine has 3 order quantities to choose from, which we will cleverly call large, medium, and small. During the fall selling season, the demand for Nicole Miller dresses will be either strong or weak. Under her expertise from past seasons, Christine has estimated that the probability of strong demand occurring during this season is 60%, and the probability of weak demand occurring is 40%. Other factors, such as industry standard, the current economy, and the behavior of competitors, can play a role in establishing these probabilities. Table 17.11 shows the expected profits during the fall season for each combination of alternative and states of nature, along with the demand probabilities in a decision table. Decision making under risk requires us to calculate the expected monetary value, or EMV, which was introduced in Chapter 5. Recall that the EMV is the average of the payoff of a particular alternative weighted by the probability associated with each state of nature occurring. The EMV is found using equation 17.2, where EMV is the expected monetary value, Xi is the payoff of the ith state of nature, Pxi is the probability of the ith state of nature, N is the number of states of nature. The EMV for each alternative is calculated as follows. Large EMV is equal to 80,000, medium EMV is equal to 55,000, and small EMV is 48,000. Because our payoff in table 17.11 are profit, we select the alternative with the highest EMV, which in this case is to order a large quantity of dresses. Doing so will result in an expected monetary value of $80,000. Let's call this expected monetary value is the expected value under risk, or EVUR. The question is this: because table 17.11 shows that there are only two potential outcomes when Christine places a large order between $200,000 to or minus $100,000, what does the $80,000 represent? The answer is that I'm looking for this as 80,000 represent the long-term average payoff of choosing a large order size over and over again. Under this scenario, the strong market will occur roughly 60% of the time, and then the weak market will occur the remaining 40%. Although this is a one-time decision for Christine, the best the EMV can do for us is to provide a long-term average profit if we repeated this decision many times. The expected value of perfect information, or EVPI. Once we have chosen our alternative using decision making under race, we can address another issue. The expected value of perfect information, or EVPI, provide us with an upper limit for how much we should pay for additional information to improve our decision. To find the EVPI, we first need to calculate the expected value under certainty, or EVUC, which is the expected payoff if we have prior knowledge about which state of nature will occur. Table 17.12 shows how to find this value. Look at table 17.12. If Christine knows that the demand for Nicole Miller dresses will be strong, she will place a large order because it represents the best payoff in the strong column, highlighted in yellow. If Christine knows that the demand for Nicole dresses will be weak, she will place a small order because it represents the best payoff in the weak column, highlighted in orange. Because the probabilities for a strong market and a weak market are 60% and 40% respectively, the expected value under certainty is EVUC equal to $200,000 times 60% plus $30,000 times 40% equal to $132,000. The EVUC represents the average long-term profit if Christine knows which state of nature will occur with certainty. We use this value along with equation 17.3 to find the expected value of perfect information. For the Gimbel department store example, EVPI is equal to $132,000 minus $80,000 is equal to $52,000. I'm sure you are wondering what $52,000 actually means. It is the most Christine should pay to acquire perfect information. That is, to know for sure which state of nature will occur. Perhaps, for example, she could commission a market research study that would give her this type of information. Recall that because Christine is uncertain about the demand level that will occur, she will most likely place a large order for Nicole Miller dresses using the decision-making under risk technique shown in equation 17.2. Sometimes the result will be a profit of $200,000 when demand is strong, whereas other time the result will be loss of $100,000. The long-term average payoff for placing a large order will be $80,000 or the EVUR. Now, if Christine had certain information about which demand level for Nicole Miller dresses would occur, she would experience some payoff of $200,000, or when she knew that demand would be strong, and some payoff of $30,000 when she knew the demand would be weak. In the long run, these two payoffs would average to $132,000 or the EPUC. How much will Christine be willing to pay for this perfect information? Without perfect information, she expects profit of $80,000. With perfect information, that number increased to $132,000. So the most she could be willing to pay to acquire this perfect information is the difference between the two, or $52,000, the EVPI from equation 17.3. Now, granted, perfect information is not usually available to decision makers, such as Christine. However, the EVPI provides an upper limit to how much Christine should pay for any additional information about future demand levels. So, for example, if Christine were to entertain the thought of acquiring additional information about demand level, say, perhaps by having a market research study done, she should do it if it costs less than $52,000. Later in this chapter, we will demonstrate a useful technique to decide if the benefit of a market study outweighs the cost.